Here it says we're going to be solving some problems using exponential growth or decay models. And you've probably done that sometime before in pre-calc or maybe in Algebra 2, where you have, maybe you're figuring continuously compounded interest or radioactive decay, and you have some amount equaling an initial value times e to some power times time. Uh, that's what we're working with here, but it doesn't look like it to start with. What it looks like is a differential equation. And this is kind of an interesting thing about differential equations. They're actually really handy ways to model these exponential growth and decay models. And once we actually try to solve this differential equation for y, I think you'll see the relationship. In terms of exponential growth or decay, it does make sense that this different kind of differential equation would work. You know, this part represents the rate of change of something. And what this is basically saying, because there's something multiplied by the function itself, this is the rate of change of the function, this is the function itself. So you could think of this as the change in the population and y as the number of things in the population. Um, how big that population is going to determine the rate, is going to affect the rate. If you have just a few people reproducing, they're going to reproduce more slowly than if you have lots of people reproducing. So that's the idea here in using differential equations to model this. I've written myself some notes because these problems can be a little bit involved sometimes. We're going to want to solve the differential equation for y, and then use these given values here. Um, Actually, we're going to use these given values to find the constants that come up in our equation, and then use the final equation to find the value that's being requested. So let me show you how this works here. This differential equation, dy dx equals 7 fourths y, is a separable differential equation. And when you do the separating, you want y and dy on one side and dx on the other side. So I'm going to multiply by dx, and that'll cancel there. And I'm going to divide both sides by y. Okay, so that's a mess. Let me rewrite it. I've got 1 over y dy on that side, and now I've got 7 fourths dx on this side. That's in a form where I can integrate both sides now. So the integral of 1 over y is the natural log of the absolute value of y. And I could add a plus c here. I'm going to add it to the other side. It doesn't make sense to add arbitrary constants on both sides. Since it's arbitrary, I can just do it on one side. And this 7 fourths is going to, the integral of that is going to be 7 fourths times x, and then plus c. So there's our plus c. Now, we want to solve this for y, and y is, well, it's inside an absolute value and it's inside a natural log. So to deal with the natural log, I'm going to exponentiate. I'm going to take e to that power on both sides. And e and natural log, they make each other disappear. They undo each other. So poof, poof, we've got the absolute value of y. And here we've got e to the 7 fourths x plus c. And here's actually the tricky bit that maybe you've forgotten in manipulating your exponents here. But if we've got a power plus another power, this is e. I could rewrite this as e to the 7 fourths x times e to the c. So when you're multiplying the same bases, you add exponents. So that's just what I've done here. Now, e to some constant, well, e is just a constant. So this whole thing is a constant. So I could take that and just put it out front here, and I'd have the absolute value of y equals c times e to the 7 fourths x. And at this point, I think what I'm going to do is just drop the absolute value. We're just going to take the positive case here and see how we go about solving this. So, so we're going to say y equals c to the 7 fourths x, sorry, y equals c times e to the 7 fourths x power. Now, what we want to do is find c here. So let's do that by using y of 0 equals 3. So that means x is 0 and y is going to equal 3. So and e to the 7/4 times 0. Well, e to the 7/4 times 0, that's e to the 0, which is just 1. So c equals 3. So I can rewrite this equation now as y equals 3e to the 7/4 x power. Okay, so far so good. What I want to do next is find y of 12. So we're going to put 12 in for x. So y is going to equal 3 times e to the 7/4 times 12 power. And just doing a little simplification here, 12 divided by 4 is 3. So this is 3 times e to the 21st power. And we don't want decimal approximations here, I don't think. Yeah, exact answers. So that's it. We've gotten the value for y of 12. Y of 12 is 3 times e to the 21st. There's another type of problem that'll pop up in this topic, but I'm going to put that in a second video.